So this lecture is concerning quantum numbers, which is basically the physical address of an electron. Remembering that an electron is neither a wave nor a particle, it's the best guess for determining where an electron is positioned within an orbital in an atom. So the way I like to teach quantum numbers is by actually showing a real physical address. So this would be the address of our school, perhaps. Then I would pose the question to you, what four items or what four categories actually given to you would describe this address? So how would you give this address if I were to only give you four items? So many people respond by saying, well, if I give you the street, okay, the city, Fayetteville, state, North Carolina, and the zip code, given all four of these parameters, you should be able to get the physical address of where we are. So quantum numbers are kind of like the same situation in terms of four numbers. So instead of street, city, state, and zip code, which sort of determine and describe an address, four numbers are going to describe the location of an electron. So those four numbers, we'll call them quantum numbers, are N, L, M sub L, and M sub S. So the easiest one is N. That's just called the principal quantum number, and that is just the period or the row in the periodic table where the element whose electron you're trying to locate. So that's very easy. You just look at an element, what row is it at? That will be its principal quantum number, N. That's the first quantum number. The fourth quantum number is also easy. It's the spin quantum number, magnetic spin quantum number. And it's either spin up or spin down. So when an electron goes to its location, it will either be spin up or spin down. So that origin comes from the fact that if you put an electron in a magnetic field, it will either orient with the magnetic field or against the magnetic field. Henceforth, this fourth quantum number can either be spin up plus 1/2, spin down minus 1/2. This L and M sub L are a little bit more complicated. This L tells you the orbital. So if L is 0, we're talking about an s orbital. So that's something you just have to memorize. If L is 1, we're talking about a p orbital. And finally, if L is 2, we're talking about a d orbital. If L is 3, we're talking about an f orbital, which I will not discuss. And finally, within those orbitals, we have certain spaces. Where within the orbital does it reside in? And that's going to be M sub L. M sub L can take on many different numbers, and that is something that we will talk about here. So the second and third quantum number require a little bit of discussion. So first of all, let's talk about the quantum number N, which is our first quantum number. That's just the row in the periodic table. So for example, if I were to determine the location of one of the 25 electrons in manganese Mn, well, manganese is in period 4 of the periodic table, so N is equal to 4. Nitrogen with 7 electrons, N would equal to 2. So as an example, iron would have a principal quantum number of 4. It is located in the D block. Oxygen would have a principal quantum number of 2. It is located in the p block. Let's talk about L here. Okay, so if L is the s orbital, notice these orbitals actually have some sort of geometry and a shape to them. So if L is 0, you're talking about an s orbital, and it looks like a sphere. Okay, so this sphere actually represents the probability of finding an electron. Remember, an electron is neither a wave nor a particle, so it's going to be the probability estimation of finding an electron or an electron cloud would take the shape of a sphere. So if L is 0, there's really only one spot for the electron to go, and it will go spin up and spin down. So L is equal to 0. By default, the third quantum number is equal to 0. Okay, that is something you'll just have to memorize. If your L is 0, we're talking about an s orbital, and M sub L, this third quantum number, automatically takes the number 0. Now within that s orbital, it's going to be either spin 1/2, spin up, or spin down, negative 1/2. Now, another thing you'll have to memorize, if your L is 1, we designate that as a p orbital. Now, within the p orbital, there's 3 slots. Okay, in the s orbital, there's only 1 slot that holds spin up and spin down. The p orbital has 3 slots. Each one holds spin up, spin down. This one holds spin up, spin down. And the third one holds spin up, spin down. Now, talking about the third quantum number, the middle slot, if we were going to call these slots, will always be 0. And then the one to the left will be -1. And the one to the immediate right will be +1. So they go in a sequential order. So the electrons in a p orbital, where L is equal to 1, this is something you'll have to memorize, can be in position -1, and it will go spin up or spin down. If m sub L is 0, it will go spin up or spin down. Usually these electrons come paired, spin up, spin down, and they march. That's when we talk about electron configuration, they march. And here, if m sub L is +1, they could go in spin up or spin down. Finally, we're going to talk about the d orbital. The d orbital has 5 slots. 5 slots, 5 orbitals. And the center orbital gets 0. And we go sequentially from there, +1, +2, and then -1, -2. So notice the shapes here. Okay, so the d orbital has these very obtuse shapes. They represent electron density. Probability of finding an electron is within these areas. Okay. Let me go back to the p orbital. The p orbital actually has the shape of a dumbbell. And right at the center of the dumbbell, we have 0 electron density. That's just called a node. Again, wave-particle duality when it comes to the electron. So that's a p orbital shape. The d orbital shape has a little bit more complicated geometries and features. Right here at the center, we have a node. We have a node here where we approximate 0 electron density. The important point here is that these orbitals have shapes. Okay, S, P, and D have shapes. Now, coming back to the L second quantum number, you have to memorize, if it's a d orbital, L will be equal to 2. This is just something you'll have to memorize. Now, where will the electrons go? They will either go in the -2 slot, spin up or spin down, -1 slot, spin up, spin down. The 0 slot, if m sub L is equal to 0, it will go in either spin up or spin down. And the same thing here for m sub L is +1 or m sub L is +2. M sub L is the angular momentum quantum number. That's the official name, but we will just call it the slots in which the electrons will go in. So now let's go back to our quantum number discussion. 4 numbers describe an electron. So if I were to describe this electron here, all right, so this represents 2p. So the principal quantum number is going to be 2. Now, what is L for a p orbital? Okay, it's going to be 1, something you just have to memorize. That's the key. L is equal to 1. That designates a p orbital. And what is m sub L? Well, this electron is at the 0, okay, the 0 orbital of the p orbital. So this would be, an electron would have an address of 2 for the principal quantum number. L will be equal to 1. The spot here is 0. And then it just so happens to be spin 1/2, so positive 1/2. So this electron here has the address of 2, 1, 0, and spin up positive 1/2. So let's do an example problem here. What are the quantum numbers for a 3p orbital? So 3p orbital is right here. So the principal quantum number n is going to be 3. Okay, it's just the number in front of the orbital designation. The orbital is actually a p orbital, so a p orbital has 3 slots and actually has a dumbbell shape. A dumbbell along x, a dumbbell along y, and a dumbbell along z. Probability of finding an electron is a dumbbell. And so what are these quantum numbers? So here we have 6 electrons that are housed in a 3p orbital. So we need 6 answers. All right. Each answer is going to have 4 numbers. Well, we know n is going to be 3. L for a p orbital is 1. Again, that's just something you have to memorize. Okay, m sub L can take on either -1, 0, or +1. And then whether it's spin 1/2 or negative 1/2, that completes the picture. So our 6 answers here, our first answer will be, so our first answer here is 3 for principal quantum number 3, 1 because 1 symbolizes a p orbital, -1, okay, and its spin 1/2. How about this electron that spin down, spin -1/2? 3, 1, -1, -1/2. Okay, how about this electron here? All right, so this would be 3, 1, 0. It's in the slot 0, and it's positive 1/2. This one would be 3, 1, 0, -1/2. And then what about our last ones? This would be 3, 1 because it's a p orbital, 1 because it's then designated m sub L, 1 plus 1, positive 1/2. This electron here would be 3, 1 because it's a p orbital. It's located in the +1 station, so 3, 1, 1, -1/2. So these are the answers, your 6 answers, 1, 2, 3, 4, 5, 6, corresponding to each electron in the 3p orbital. Okay, how about for a 4d orbital? All right, so remember, a 4d orbital, just like a 3d or a 5d, holds 5 spaces for a total of 10 electrons. So we're going to need 10 answers here. All right, so our first one is the principal quantum number, which is 4. Okay, so that's your n. L for a d orbital is going to be 2. Okay, so that's, again, something you just have to memorize. And now, where are the slots, the m sub L? So we have, for example, 4, 2, -2, and this is +1/2. This electron here would be 4, 2, -2, -1/2. Shown in green here would be a 4, 2. Now it's located in -1, and it's spin up +1/2. The next one would be 4, 2, located in -1, -1/2. How about the center one? It's going to be 4, principal quantum number. 2 is L, because L equals 2. That's how we designate a d orbital. And it's located in position 0 of the third quantum number. It's +1/2. Its pair would be 4, 2, 0, -1/2 spin down. This one here, shown in yellow, would be 4, 2. It's located in the +1 orbital. So 4, 2, 1, +1/2. Its partner would be 4, 2, 1, -1/2. Finally, our last one here would be 4, principal quantum number, 2, designating the d orbital. M sub L is +2, and this is +1/2 spin down. Its partner is 4, 2, 2, -1/2 for spin down. So 10 electrons, 10 quantum numbers, each one containing 4 terms. These are the addresses of all of the electrons, individual electrons in a 4d orbital.